Greetings. Today we'll be discussing about effect of yielding of supports on determined and indeterminate trusses. First, we will try to understand what is the meaning of yielding of supports. Yielding of support is nothing but sinking of the support from its position. This may be due to the applied forces, heavy applied forces, or may be due to the geometric constraints or release of the geometric boundary conditions. Due to yielding of support, the member will be subjected either towards the tensile effect or the compressive effect, thereby leading to the generation of internal stresses in the member. In case of statically determined structure, the members are able to restore their deformation or distortion, whereas in case of indeterminate structure, the members are rigidly connected, or sometimes we can say the complex geometry is there. That's why this deformation may lead towards the development of internal stresses, which may lead towards the failure of the structure. Now, how to analyze such a structure, that is how to analyze an indeterminate structure, becomes a complex job here. For that, the simple steps we are going to follow here. Very first step is that we will consider the force corresponding to yielding of support as a redundant force, or the reactive force which has been developed at the end resistance, which has been released as a redundant force. Then we will obtain the basic determinate structure by removing the constants that are yielding supports, and then we are going to find out the magnitude of the redundant force and its effect in all other members. The geometric condition of deformation of the yield support is considered as a displacement corresponding to the effect of that redundant force. It is considered, it is denoted as a dx. When support sinks downward, we are going to consider the value of dx as a positive, and when support moves upward, we consider the yield value as a negative, as a positive. Okay, and vice versa. After knowing the redundant force, we'll apply the concept of strain energy here by using Castigliano's second theorem by maximizing the value of the redundant force by taking partial derivative of total strain energy possessed by a body under the effect of redundant force with reference to the redundant force, and we will try to maximize or minimize that value. And finally, we will write an equation where we say deflection at a caused by a particular load, we can be find out as a partial derivative of strain energy with reference to the force under which displacement is desired. So with this concept, we'll move towards the analysis of the structure which is subjected to such a case. Numerical number 17, analyze the truss supported as shown in figure. If support B sinks by 3 mm, take E is equals to 200 GPa. Cross-sectional area of each member is 50 cm square. The given truss is a 2-bay frame having end support A as a hinge support, at B roller support, at C roller support. The frame is having bay width about 4 meter. Both the bays have the same width, as well as the height of the bay is given about 4 meter. It is supposed that the support B sinks by 3 mm, and what will be the effect of this sinking among the other member forces. As per our consideration, we will consider first the geometric constraints of this one, and we will find out whether the structure is determinate or indeterminate. We know that degree of static determinacy is composed of two parts, external indeterminacy and internal indeterminacy. So in case of yielding of support, most the things will dominate related to the sinking of support, means external indeterminacy will be the focus of matter here, irrespective of the internal compatibility of the member forces. So here DSE, if you want to find, it will be R minus 3 unknown reactive forces minus the available equilibrium equation, or we can say usable equilibrium equation. So in case of coplanar force system, we have 3, that's why we get reactive forces are 4, 2 at end A, 1 at end B, and 1 at end C. So we have 4 minus 3 equals to 1. Externally it is indeterminate. When we talk about the internal compatibility, we have equation DSI equals to M minus 2J minus 3. We have 9 members and 6 joint. So it comes to be 9 minus 2 into 6 minus 3. resulting into a value of 0 means it's internally stable. So degree of static indeterminacy is purely governed by external reactive forces. One reactive forces is unknown. Let us consider joint B is being synced and RB, the reactive component which is being produced due to end restraint at joint B, as a redundant force here. So what we will do, we will remove the joint which is causing yielding of that support. So we will remove it and the structure will become statically admissible. Once we got a structurally admissible structure, we are supposed to find out the reactive forces. Seeing the geometry here, there is no external loading. So reaction Ra and Rb will be equal but opposite in action when we consider only the effect geometry and constellation. If I say at the joint B, I am going to apply a unit load to know the effect of redundant force as X, then what will happen, Ra and Rc will come in terms of a X as a 0.5 times of X due to symmetry in the geometry and symmetry in the loading. Once we got the reactive forces, then the second part is we want to find out the coefficient of contribution of this redundant force in other members. Let us say K1, K2, K3, K4, K5, K6, K7, K8, K9. These are the respective coefficient of distribution of this redundant force among the other members. Now our interest lies to find out the value of this K components, K coefficient. So for that we will go with the analysis part. We will analyze the structure by joint method. Let's start with the joint F. At joint F we have two member forces and there is no external loading. To balance them one, so some resultant equation along x direction, resultant equation for equilibrium of forces along x direction yields to minus K4 minus 0 equals to 0, hence K4 equals to 0. Similarly, there is no vertical force to balance the K1 value here. By typographical mistake, it comes to be K3, read it as a K1. So K1 minus 0 equals to 0, K1 comes to be 0. After knowing the member forces at joint F, we will move towards the second joint, joint A. At joint A, we are having 5 forces, among which HA and K1 bears a value equals to 0. That's why 3 will be playing role in equilibrium here. The member force K3, member force K2 and the reactive force 0.5 times of X. Here we have considered the vector to balance the effects of the reactive force and the component parts here. One may have the different types of vectors assumption here. Now if we apply static equilibrium equations towards this free body diagram, we get summation of Fi equals to 0, K2 sine of 45 going downwards, it should be a negative value, plus 0.5 times of X equals to 0, resulting into a relation K2 comes to be 0.707 times of X. Similarly, if we move towards the static equilibrium equation along horizontal direction, we get a relation minus K2 sine of 45 degree, the component going towards the left hand side, plus K3 equals to 0, resulting into a relation K3 equals to 0.5 times of X. Now if we go move towards the joint B, we have 4 forces at the joint B. One is the applied external redundant force capital X, and the K3, K4, K5, the member forces. Among this we know the K3 value from the relation summation of forces in x direction equals to 0, minus K3 plus K9 is equals to 0, hence K3 equals to K9, which equals to 0.5 times of X, tensile in nature. Similarly, if I write summation of forces in vertical direction, I get K5 minus X is equals to 0. K5 comes to a value of X in tensile in nature, X kilonewton tensile in nature. Now from the symmetry of the loading and symmetry of the geometry, we can make a statement here. K4 is equals to K6, member force K4 equals to member force K6, which equals to 0 kilonewton. K1 is equals to K7, which comes to be 0 kilonewton, and K2 is equals to K8, which comes to be 0.7071 times of X. Once we have done with the finding of the coefficient of the forces of distribution of redundant force, we'll try to find out redundant force which we want to apply on the joint which is under sinking here. For that we will have tabular formatting of the results which we have. Very first column will have members will be written in a sequence, like I have taken first periphery members AF, FE, ED, DC, CB, then I have taken vertical members BA, B, and then the bracing member AE and EC. Their respective lengths has been mentioned with reference to geometry which has been given to us. Then we have area of cross section of each member. All the member area has been given constant. It's about 500 mm square. E value is given to us. It's about 200 GPa. Now we have find out the K values with reference to the applied redundant force at the member AF, FE, ED and DC. They are going to carry zero forces. That's why it has been mentioned here 0. CBBA, they are going to carry 0.5 times of X. That is a tensile in nature. That's the negative part. BE is negative times of X. This is redundant. This is the braced member which will carry the force in tensile nature minus X. Sorry, it's not a braced member, it's a vertical member. AE and EC, they are having a value 0.707 times of X, 0.707 times of X. Both are in compressive, that's why positive values has been assigned here, positive sign has been assigned here. Then we require product K square L upon A. If we do the product of fifth column, squaring fifth column, multiply by length and divided by cross section area of respective member, we get the resultant product value as 0 0 0 0 for first 4 member, because force carried by the member is 0. Then CB, it will be 0.5 square multiplied by 4000 divided by 200 and so divided by 500, resulting into value of 2x square. Similarly, we can go for the product for member BE, and final what I will do, I will take a summation of all values here, K square, summation of K square L upon AE. As we know that strain energy stored up by the system will be given by a relation x square L divided by 2 AE. So we get answer here 23.3 x square divided by 2 E. I am not substituting the value of A here because already I have taken A in product. Now we know the support B has been synced by 3 mm. Then we can write this relation with reference to Castigliano's second theorem, which states that partial derivative of strain energy with reference to redundant force is equals to the displacement caused by that particular force. So we can get here 23.x divided by E, the relation we will have here. 23.x is how it comes. X square will yield to a value of 2x. 2 at the numerator side and 2 at the denominator side, they will get cancelled. What remains here 23.x divided by E here. See here E has to be supposed. So please read it as a divided by E. Then after rearranging the equation, we are interested to know the x value. X will come to be 200 into D value we have 3 mm divided by 23.3, leading to redundant force value about 25.75 kilonewton. Likewise, we will get the redundant force which is being developed due to sinking of the support B. Once we have got the redundant force, we will put this redundant force contribution to find out the final forces, which will be equals to P plus K times of X. P is absent here because external loading is not there. So only product X, K into X will be there. So for the first 4 members, K value is 0. The resulting value will be 0. In the second one, we have the K value as a minus 0.5. Multiply by 25.75, result into value 12.875. Negative sign is there. That's why nature is considered as a tensile. Likewise, I will do the calculation for individual member, and this product will be displaying what the final forces the member will carry under the action of yielding of the support. With this, we complete the part related to the yielding of support. Hope you understood. Also, I have completed the module related to the your analysis of trusses, both determinate and indeterminate. So please, with this I will end my lecture. Please stay at home, be safe and be healthy. Thank you.